Hi, and welcome to AP Chemistry Exam Review. It's me, Dr. V, and I'm here to help you get ready for the AP Chemistry exam in May. We're working today on free response question number 2 from the 2017 release exam. It's one of the long free response questions, and that means it was scored out of 10 points. There are a lot of parts to these long free response questions. I always recommend that students try to work through the entire problem on their own. You can do it part by part, but you want to have a solution for each part before you listen to my explanation. That's really what's going to help you most develop as a student. To do that, you'll need your calculator and your periodic table and your formula sheet. And then you can keep track of your score as you go, and then think about how you need to enhance your answers if you didn't earn all the points for each part. So let's jump right into the problem. We're given two possible Lewis structures for fulminic acid. We have a left structure and a right structure. And part A asks, explain why the diagram on the left is the better representation for the bonding in this molecule. Justify your choice based on formal charges. So that's really the key to this whole question. It's really all about formal charges. It was scored out of 2 points, and I'll talk about what we need to do to earn both points for part A here. So it's a formal charge question. The first thing we need to do is assign the formal charges to all the atoms in both molecules. To calculate formal charge, we start with the number of valence electrons for an isolated neutral atom of that element. We subtract the number of bonds, which is the number of lines attached to it. And then we subtract the number of non-bonding electrons, which is the number of dots attached to it. So we're going to do this for each atom in both molecules. We'll start with the left-hand molecule. For the hydrogen, all right, it has one valence electron. All right, it's got one bond attached to it. There's no non-bonding electrons. It's got a formal charge of 0. Once we calculate that, we write a 0 above the H and we circle it. It's the convention. It's fine. We'll go on and do that for the other 3 atoms. So for carbon, we also get a formal charge of 0. 4 valence electrons, 4 bonds, no non-bonding electrons. For nitrogen, we get a formal charge of +1. Nitrogen has 5 valence electrons. There are 4 bonds attached to it, no non-bonding electrons. And then finally, the oxygen has a formal charge of -1. 6 valence electrons in an isolated atom, 1 bond, 6 non-bonding electrons for a -1 formal charge. As a check for myself, the sum of the formal charges should add up to the overall charge of the species. It's a neutral molecule, so the charge of the overall molecule is 0, and the sum of the formal charges is 0. So that's reassuring that I've done that correctly. Let's go on and do the same thing for the right-hand molecule. The hydrogen, again, has a formal charge of 0. The carbon here has a formal charge of -1. 4 valence electrons, 3 bonds, 2 non-bonding electrons for a formal charge of -1. The nitrogen has a formal charge of +1, just like we saw in the left-hand molecule. And the oxygen here has a formal charge of 0. 6 valence electrons, 2 bonds, 4 non-bonding electrons. Okay, so the first thing we needed to do, right, was to assign all the formal charges, and that's what we needed to do to get the first point. You really don't have to show the math setups to do the calculations, but assigning the formal charges correctly was the first thing we needed. And then we can talk about how we can use this to compare the two structures. All right, so when we're doing formal charge based evaluations of molecules, we look for 2 things. One, we look for formal charges as close to 0 as possible for all the atoms. Closer to 0 is better than values farther away from 0. Both molecules have formal charges of 0 and 0 and +1 and -1. So that really doesn't help us distinguish between them. But the second criteria is really helpful. We want the negative formal charges, if you have to have one in a molecule, to be on your more electronegative atoms. In our left-hand molecule, the negative formal charge is on an oxygen. But in the right-hand molecule, the negative formal charge is on a carbon. Oxygen is more electronegative than carbon. It's preferable, based on formal charge arguments, to have our negative formal charge on oxygen than on carbon, and that's why the left-hand molecule is the better representation, or is the preferred structure. And that's what we needed to say for the second point here. Okay, let's go on. Fulminic acid can undergo an equilibrium to produce isocyanic acid. We're given the balanced equation, noticing that there's 1 molecule on each side of the reaction. We're given their Lewis structures. And we're given a table of bond enthalpies. And part B says, using the table and the balanced equation and the structures, find the value of the enthalpy change for the reaction. Okay, so to find the enthalpy change for the reaction, we're going to add up the bond enthalpies for all the bonds that we break. We're going to then subtract the sum of the bond enthalpies for all the bonds that we form. So it's broken minus formed, and that's how we do these problems. I'm actually going to put this on the next slide because otherwise the slide's going to get too busy. So we're thinking about broken minus formed here. So the bonds we have to break in fulminic acid, we have to break an HC bond, a CN triple bond, and a nitrogen-oxygen single bond. In terms of what we need to form, I need to form one HN bond, one NC double bond, and one CO double bond. All right, so I need to add up all the bond enthalpies of what I'm breaking, add up the bond enthalpies of what I'm forming, take the difference. All right, so I just go to the table and I pull that information out for the HC, the CN, and the NO bond, the CN triple bond specifically. And then for what I form, I have to form an HN bond, I form an NC double bond, and I form a CO double bond. And I put those together and I take the difference. Do you pay attention to order of operations when you're doing these kinds of problems? It's not that they're very difficult, but it's very easy to misenter things. So I definitely would write it down, have that supporting work. All right, and so I get a delta H of reaction of minus 246 kilojoules per mole. It was basically 1 point for figuring out what you needed to break and form, and 1 point for doing the math correctly and getting the correct answer. Very reasonable. All right, let's go on. The problem continues. These long free response questions. A student claims that the entropy change for the reaction is close to zero. Explain why the student's claim is accurate. This is a really nice way of probing your understanding of delta S. All right, so going back to the balanced equation where we have one reactant molecule and one product molecule, all right, they both have one molecule, both molecules have the same number of atoms, they're both in the gas phase. There's really nothing here to have significant effects on the entropy for the reactants versus the products. There's no change in the number of representative particles, there's no change in the state of matter. Right? We know that if there are more particles, that leads to an increase in entropy because there's more possible arrangements, right? With no change in the state of matter, right? We're not changing from liquids to gases or solids to liquids, right? We know that liquids have more possible arrangements or microstates than solids, and gases have more possible arrangements or microstates than liquids. But we don't have that change here, and therefore we would not expect to see a significant change in delta S. It's going to be very, very close to zero. So I do want to just point out that when you're talking about entropy, the College Board really likes this term microstates, right? It's a better term. It's a little more sophisticated than talking about increased randomness. So if you can squeeze that into your answer, that's just going to enhance your answer, right? And that's what we needed to write down for 1 point. Which species, fulminic acid or isocyanic acid, is present in higher concentration at equilibrium? Justify your answer in terms of thermodynamic favorability and the equilibrium constant. So we have to think about delta G and K here and how they're related. So we had determined a couple of parts back that the enthalpy of reaction was minus 246 kilojoules per mole. And part C asked us about delta S and told us that delta S was approximately zero. So if we think about the formula for Gibbs free energy, delta H minus T delta S, all right, the delta S term is zero, so the T delta S term basically drops out. And so the Gibbs free energy value is going to be very close to the value for delta H for the reaction. So it's about negative 246 kilojoules per mole. That means we have a negative delta G value, and the process is thermodynamically favorable. Since delta G is less than zero, that means K is going to be significantly larger than 1. Right? And that means products are going to be favored at equilibrium, right? Because that's what a very large KEQ value means. You have more products than reactants at equilibrium. If we go back to our balanced equation, our product is isocyanic acid, and therefore we can conclude that there's a greater concentration of isocyanic acid at equilibrium. That's what we needed to do. There was a 2-point question. So we needed to determine that delta G was negative, and therefore it's thermodynamically favorable, and the relationship that delta G is less than 0 means K is greater than 1, which means there's more products. And so coming to the statement that there's more isocyanic acid at equilibrium is what you needed to do for the second point here. The ammonium salt of isocyanic acid is a product of the decomposition of urea, which is shown here below. A student studies the decomposition reaction at 90 degrees and collects data as a function of time, the concentration of urea as a function of time, and here's our data. So we have a table of data and a graph of that data. Okay, so let's get to the actual question here, right? We've jumped to a new topic. We're now going to be doing some kinetics. The student proposes that the rate law is the rate equals the rate constant times the concentration of urea. So what I'm noticing about this is that the rate law is written here as first order. All right. Explain how the data supports the student's proposed rate law. Well, again, the rate law is first order in urea. All right. And the hallmark of a first order reaction is that the half-life is a constant interval and it doesn't change even though the concentration of reactant is changing. So if we go back and look at our data table, all right, it takes 10 hours for the concentration of urea to drop to half of the initial concentration. And then it takes another 10 hours for it to drop by half again, and another 10 hours for it to drop by half again. It's a constant half-life with a constant interval of 10 hours. All right. And so that fixed interval is what backs up our statement that the rate law is first order in urea. Okay, so that's what we needed to say for 1 point, that the data support that because the half-life is constant. We don't have to say that it's 10 hours at this point, but believe me, it's going to come in handy. So, using the proposed rate law and the student's results, determine the value of the rate constant K. Include units with your answer. You know, they often ask about units with rate constants, so always be prepared to do that. Now, we know it's first order, and we also know that the half-life is 10 hours. We had already determined that. If you go pull out your formula sheet, we know that for first order reactions, that the half-life is equal to 0.693 over K, the ln of 2 over K. Well, we can easily rearrange that to solve for K, where K is 0.693 over the half-life. So 0.693 over 10 hours, we get a rate constant of 0.069 to inverse hours. So you want to be careful about your units. It's a first order reaction. Your units for the rate constant should be 1 over time. Since we're working with time, it should be 1 over hours, or hours to the minus 1. And that's what you needed to put for 1 point. Okay, the problem continues. Of course it continues. It's a long free response question. The student learns that the decomposition reaction was run in a solution with a pH of 13. Describe an experiment, including the initial conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on the concentration of hydroxide ion. Okay, so really what they want you to do here is describe the method of initial rates. So you're asking, how much does the concentration of urea change in a certain amount of time, right? That's the measurement that you're going to make. And does this change if I vary the concentration of hydroxide, which I can alter by changing the pH of the solution? So what I want to do is run at least 2 trials where I keep the initial concentration of urea constant and all my other variables like temperature constant, and measure the rate of decomposition of urea. We can do it at the pH of 13 where I know the hydroxide ion concentration, and then measure the rate of decomposition of urea at a different pH where the hydroxide ion concentration is different, and see if that affects the rate. All right, and that's what you need to discuss to get the 1 point for this part. So they want to see that you're familiar with the setup for how to do kinetics experiments, and the easiest way to do that is the method of initial rates. How did you do on this problem? So out of 10 points, right, some of them were fairly easy, some of them were very involved. If you know your kinetics well, if you know Lewis structures and formal charge fairly well, it's a very manageable question. But the average score on this question in 2017 was just over 3 points out of 10. So if you scored 3 points, you're right on the national average. If you did 4 points or more, you're doing well, and you should be pleased with yourself. But you always want to make sure you've got those core skills. Kinetics are an important topic. Bonding, Lewis structures, formal charge, also important topics, things you want to make sure that you know well. If you haven't already subscribed to my channel, I encourage you to do that. I keep making more videos. I want you to do well on your exam. Have a good day.